is we'll get through chapter 10 quite quickly. We'll finish off the discussion of alkynes. We'll start again talking about synthesis, how to use these reactions to actually do things and to make interesting compounds. And then I'll be into 11. And just when things were getting comfortable, we got through 9, big sigh of relief. Everybody's happy about getting through 9 because it's huge. We got through 10. 10's kind of friendly, kind of gentle. And all of a sudden, 11. And 11 is very different because it's all about radicals. It's a very different type of idea from carbocations. We've got to be careful. So no recitation quizzes this week. Some time to talk to you. I'll be here tomorrow. I'll be here Thursday. Make sure we get these problems solved as soon as we can. Again, if you're not here Wednesday for recitation, feel free to come to today's classes or come and find me at other times. Now, the idea of alkynes being used to add water should be similar to the addition of water to an alkene because they both have pi bonds. So in the first step here, if we recognize aqueous acid is going to be a polar system, so we should expect a polar mechanism with intermediates such as carbocations. We can see very simply at the beginning, picking up a proton here in a proton transfer step. After you do that, you generate a carbocation. Now, in many of these alkynes, just like an alkene, you have a choice of where to put that proton. And again, you're going to make the decision based on which is the better outcome, which is the better carbocation that I can form. In this case, this is kind of like a secondary-like carbocation. It's not as bad as the carbocation at the end of the chain, so this will be preferred. And then in that next step, what we'll expect to happen is nucleophilic attack. The water comes in from the solvent, and it attacks the carbocation to actually trap this thing, just like it would from Markovnikov addition. Then we get this protonated species. This will have to lose a proton back to the solvent. Molecular water can come in and do that. And we'll end up with this guy. Now, I've said in the past, this is the formal product of addition of water to an alkyne. But it isn't the product that is isolated. And that's what gets complicated here because we start to get these hidden processes that you have to be aware of to get to the actual outcome. So in this case, the enol, right there, is not as stable as the ketone. You'll see a lot more of this next term. You'll see it in biochemistry. We see this changing. We see this transformation from the enol to the ketone, especially in the presence of acid or base. So in this case, we have acid, and we should be thinking logically now. I have a double bond right here. That double bond, when it was an alkene, picked up protons. That was the whole point of Markovnikov addition. So it ought to do the same thing here. We have an alcohol that can pick up a proton and go backwards. That's why we have this reversible arrow. But if we think about going in a forward direction, I can put a proton onto the double bond. And so what will happen now is this will go after H3O+, it will pick this up, and we'll do essentially a Markovnikov addition. Now, this is really what's new in this section. This idea of this heteroatom stabilized carbocation. This is a very good system because the charge is next to an electron-rich atom. Even though the oxygen is more electronegative, it will help out the system by sharing a pair of electrons. If we drew the resonance structure for this, we'd get the next picture in line. And you'll see now the application of all of the arrows that we see in chemistry. And the whole point here is that this picture looks better than this picture because every atom has its full complement of electrons. You're not disobeying the octet rule like you are down here, it only has 6. So at the top here, we're looking at deprotonation, and that finally gets you to the product. So we now have the sort of IKEA idea where everything sort of is modular, everything fits together, and that is a separate mechanism in its own right, and this is a separate mechanism likewise, right? We're starting to piece things together to make more complex systems. So in the presence of acid, you expect addition to an alkyne. You've got to be on top of things. If you have a terminal alkyne, you'll typically get one product in which the ketone is formed. If you have an internal alkyne, you'll get 2, and you'll get mixtures. So this system is internal. We expect to see 2 products by addition of H2O across the triple bond, I should say, in either direction, and that gives 2 different ketones. If you have a terminal alkyne like that, and you can recognize it, that will give you primarily 1 product because the other one is going to be through a primary like cation, not so good. And so we expect to get the internal product, which is the ketone. At the bottom, we see more complex, yes, but nothing else is going to happen on the left in terms of chemistry. The acid will react with the triple bond. You'll get addition of H2O. In this case, it will go to give you the more substituted product, which will be the ketone, like that. So practice, there are problem sets out there. There's all the stuff I put on my website, some of which will go away next semester, some of which will be redone in different ways, but use it, or else I won't be doing it anymore. Now, the opposite regiochemistry here, just to get us back on track because it was the weekend. We now start to play games. You'll now start to see in the quizzes and on the homeworks questions that are asking you to make a molecule. Here's the product that we want for whatever reason. Let's make it. And you have to be on top of things to be able to use the toolkit, to be able to use the right chemistry at the right time to do this. So what we've got here, alkyne, and we're trying to turn it into an aldehyde. And what we'll do here now is try to put the hydroxyl group on the end there. So just like we did for the alkenes, let's use the hydroboration chemistry because that will then put the boron on the less crowded carbon. And you get the opposite regiochemistry to what you did for the acid catalyzed process. So we're going to get this, which is the same process, just add the boron to the less crowded end, add the hydrogen to the more crowded end, and you get this, and this is an enol. Now that enol will convert under these conditions to this guy. This is an aldehyde at the end of a chain. The slight difference here is that you're under basic conditions in the second step. So the mechanism for this isn't the same as the one for the acid. And we're trying to keep a track of these things and catalog them in recitation and office hours. If you are under acidic conditions, your intermediate species will be positive. If you're under basic conditions, your intermediate species will be negative. So this is basic, no doubt, because of the hydroxide. And so we expect negative thing, deprotonating, making a negative thing. This is possible because this is resonance stabilized. And there you can see the sort of formation of the carbonyl. The carbonyl is starting to reveal itself. If you pick off a proton from the solvent, you end up with the aldehyde. So that's a very different mechanism, and it is worth learning both of these things right now because they come back in the second term. And the second term is 95% mechanism, 5% spectroscopy, right? So it's all important here. So we have this idea now of picking and choosing, deciding on what you want to do. Chapter 12, when we come back after Thanksgiving, is all about the decisions you have to make to put a molecule together. It's quite challenging, but fun. We have the addition of water under the acidic conditions, that can give you the ketone, or addition of water under hydroboration oxidation conditions can give you the aldehyde. They are really important second semester compounds, so now we have ways to get there. We're on our way. Anybody want to say anything? What's happening out there? Anybody see that Bond film? Nobody goes to the movies anymore? Next year is 20 years since I last went to the movies. Anyway, we're going to add things now. We're going to add things across alkynes. This is not so interesting in the sense of the products themselves, but what can you do with those products? We have the possibility here of adding halogens, adding X2, chlorine or bromine. And we've got to be careful here answering quiz questions and answering homework questions. Make sure you read the question thoroughly. It might ask you to add one equivalent. That means 1 mole. You might stop at the alkene. But if it asks you to add an excess, you're going to go further and add back to that alkene again and get the saturated compound. So halogenation of alkynes is pretty straightforward. It's a nice way to put X groups on here if we want to use them as leaving groups in different conditions. But if we have an excess, here's the key here. Add 2 equivalents, and you'll add to each carbon twice. Down here, if you're said to have 1 equivalent, that just means you've got a limited amount of the halogen. It only adds once, and you get these isomers here, and you get an alkene. Now that's not particularly interesting in its own right, but it is useful to be able to go further from there. Ozonolysis, like we did for alkenes. I've had some good questions about ozonolysis. We'll talk about it in recitation today. Wednesday class, again, come find me. I can show you some shortcuts. I can show you some tricks to what to look for in this system that's not as bad as it looks. We can see now ozone ought to react with an alkyne just like it did with an alkene, and it does. Except you can imagine now with 2 double bonds there, it can go further. And you can imagine here, we can break this thing apart, not to aldehydes or ketones, but to carboxylic acids. And have a go at that mechanism, see if you can do it. It's similar to the one we already did. If you have a terminal piece here, you end up with a molecule of carbon dioxide. And so basically you're cleaving apart these 2 pieces in the same way we did with the ozonolysis on the alkenes, but you're going to a more oxidized system because you have more double bonds. So keep an eye on that one. It's useful. We've already done that mechanism. Now, the end of this chapter is all about building towards 12. It's all about starting to use alkyne chemistry to actually make more important things. And you'll find now, as you start to study, if you've been keeping up, this can be fun. If you haven't, it's just a mess. We have a molecule here, a terminal alkyne. What's the approximate pKa right here? 25-ish, right? 25, 26, right? It's not acidic unless you put it in the presence of a powerful base. And that powerful base could be something like amide, NH2-. And that NH2- now will go after that proton, and it'll produce what you might call an acetylide or an alkynide anion. This species is really useful to us. You don't see it in biology. It's too basic. It wouldn't form in water. But you do see it in the organic lab as a nice way to knit together carbon pieces. So we'll now produce this to go someplace else, and we're starting to build up towards this idea of construction. What we'll do next is this. Anybody want to tell me what that mechanism is? Early on a Monday morning, what is that? Anybody? You've got a negative bit going after some carbon, kicking out some X group. What is that? Nucleophile is a good word. Anybody else? It's an SN2, shoots and scores. That's an SN2 reaction every day, all day, 7 days a week, right there. Bimolecular substitution, replace one piece with another. So we've now generated a very powerful nucleophile, which is also basic, yes. So you can't do this in protic solvents. You have to use aprotic solvents to avoid reprotonation. But look at this. We've gone from a terminal alkyne and turned it into an internal alkyne. Well, big deal. but you've basically extended your chain. And this is the only way we've really seen how to do that. And if most organic and biological molecules are made up of long carbon chains, this is a nice method to be able to do this, to get places. So this is now the alkylation of terminal alkynes to make bigger alkynes. And then once you've got that bigger alkyne, away we go. So we could turn this thing into, example, alkanes. If I want to turn this product into an alkane, what do I have to add? H2, right? With what? It doesn't just happen with H2, what else do you have to add? A catalyst, right? And if I want to do this and turn it into a cis-alkene, what do I add? Lindlar's catalyst. If I want to turn it into a trans-alkene, what do I add? Sodium ammonia, right? So we've got those things hopefully up here now. We can start to use those. So this is now an entry into molecular construction, molecular engineering, whatever you want to call it, simply by doing an SN2 reaction to make a carbon-carbon bond. This is very, very powerful. So here we go. We can start off with this alkyne. It has to be a terminal alkyne because internal alkynes don't have acidic protons right there. It has to be at the end of a chain. And if we take that with a base, we can do a two-step sequence. And I will say again, in these sequences, I want to see products from both steps. I'm not asking for mechanisms. I'm asking you to give me what you expect to get from that first reaction when you mix sodium amide with the alkyne. And it should be a acetylide anide. It should be the negative charge on the carbon. In the second step, that process, that product then reacts with the alkyl halide to do an SN2 reaction. And so what we've got over here is a combination of 1, 2, 3, 4, 5, 6, 7 carbons to make a 7-carbon chain. Now I did promise at the beginning of the term that we wouldn't have to count past 4, but we will. Okay, we might have to even get to 15, so we'll have to be on our toes here. Here we go, sequences. This is in the quiz, it's on the homework, that's online, be careful. In the first step, take that proton off, recognize a strong base, make the carbanion here, make this thing negative. You got rid of the proton in the first step, then you do an SN2 reaction. Now let's talk about that. This is somewhat limited. There are some limitations to what you can do here. So what type of alkyl halides can I use? Primary and secondary, why not tertiary? Too sterically hindered. What would they do instead if you can't use a tertiary halide? They would do an E2 instead, right? So it's starting to make sense. It's logical. This is limited to methyl and ethyl and primary systems. Some secondary you'll get away with. But as you start to crowd around that electrophile, just like in the SN2 chemistry we did a while back versus E2, you start to get more E2. So this now is starting to get realistic. But in this example where I have a primary system here and a primary system here, it's a very, very simple, very elegant way of making a larger alkyne, a longer chain alkyne. Bear in mind, for you people who don't like to think, we're now going to ask you to think backwards. Next semester, we ask you to think backwards, inside out, and upside down, all at the same time, while standing on one foot. Right? At the end of 3720, you'll be able to do stuff. We've got to think now going backwards. If I had to make this molecule, what would I use? Start thinking of that sort of context. I've got to think now, I need to put this ethyl group on, I need to put this methyl group on, I need to plan by deciding what reagents I have to use. More of that to come up in the near future. So let's think about this. You should, at this point, this is what, the 12th week of term? We've been doing this for 3 months now. A long time. You should recognize this stuff straight off as what? What type of reagent? It's a base. It's a very powerful base. And you should recognize THF as what? It's a solvent. What type of solvent? It's polar aprotic. It certainly is. So they are appropriate conditions to be able to do a acid-base reaction in which we go after this thing, take this thing off, and make this carbon here negative. And then at that situation, after we're done with that, we put the methyl bromide in, and we expect the product. Now, count. 1, 2, 3, 4, 5, 6 carbons in the starch material. How many carbons in the product? 7. It's that simple. Keep an eye on that, and we should be able to get a product easy enough. Why no cis and trans? Any cis and trans possibilities here? No, because it's linear, and you just can't do that. You don't have the setup to do that. Okay. Bit more sort of stuff down here, but this is the only acidic proton in that molecule, so let's take it off. DMF, go back, look at it, polar aprotic, good for these types of reactions. We can take off the proton at the end right there, and then we can attack. Now, I've got 1, 2, 3, 4, 5, 6, 7, and how many do I expect in the product? 10. So be very careful. This is analogous to me with the Newman depiction we did a while back. People would be given a molecule that had 9 carbons, and they'd end up with 11. Not because they can't count, but because they didn't do the studying and they didn't realize that some of the carbons are already involved in the Newman depiction. And likewise here, that's a carbon and that's a carbon. And you can only pick that up by putting the effort in. That's all you can do, is put the effort in, see enough of these things, and get comfortable with them. Because I think now these are the most important compounds for 3719 to be able to think about what we do in 3720, which is knit carbons together. So there's the product. No concern about cis or trans. All that stuff on the left was just there to annoy you, or to confuse you, or to distract you. And everything that happened on the right, and you got that molecule. Now down here, again, is anything going to happen down here? No. And let's think about the conditions in the first step. We haven't seen that molecule before. We see a lot of it next term. We're going to see the deer antlers and nitrogen with a negative charge. That's a very powerful nitrogen base. It's pretty much the same as this one above it, except it's organic soluble, very much so, and it's also bigger. So it's non-nucleophilic. We see that again next term. That's a very powerful base. Why doesn't anything happen over here? Why not just attack some of these things over here? Don't know. Monday. Haven't woke up yet. Why not attack over on the left? Not because it's large. Not because it's not flat. I've got all day, mate. I mean, we can be here all day. Go on, keep going. Electronegativity. No, it's not that either. Well, kind of it is. It's all to do with electron density, right? Are there any delta positive, morning Mike Mark? Are there any electron poor regions in that molecule? No, it's all non-polar, so don't attack it. The only thing that you can possibly attack is this acidic proton. So you take this thing off, and all of this stuff will be kept in the product, and we'll add this longer chain. At the end, it's an alkyl primary system, and we get a more elaborate product. It's molecular Lego, that's all it is. Anybody? Who's missing today? The chemical engineers are missing, aren't they? Some of them are. Where are they? Out of town, I think? Okay. Right, let's put this together. The last section in this chapter, before I move into 11, is using this to build stuff. If you like solving puzzles, this can be fun. You've now got the toolkit to do a pretty large amount of chemical synthesis. 11 will add on to that, but now we can start building things. So if you want to make an alkyne, you can do it several different ways. You can eliminate from halogenated species, or you can do what we just did and knit things together. If your product contains the same number of carbons as your starting material, you're doing simple functional group manipulations, adding X, eliminating to make an alkyne. If your product has more carbons than what you start with, you're doing the substitution reaction we just did. Deprotonate, then alkylate, and away we go. You can then turn, as we just asked, we can then turn these things into alkenes quite easily, or we can go all the way to alkanes. And we now have this sort of very, very useful group of reactions to be able to go very different places. So this is where things will pick up and things will change. So, look at this system. From now on, you'll be asked these questions. You have to plan the synthesis. You have to come up with a method to get from left to right. You look at this molecule, you look at this molecule. This is what we want. We would like to make this for whatever reason. What's the first thing you do logically here? Somebody said it. Come on, say it. You count the carbons, right? Because that's the most logical thing to do. Last year, it took me forever to get that out of the class. You count the carbons. Over here, I've got 1, 2, 3, 4, 5, 6, 7, 8. Over here, I've got 1, 2, 3, 4, 5, 6. So what piece do I need? How many carbons in my electrophile? 2. See how it works? Yeah? You need 2. So I need a powerful base to take off the proton, and then I need a 2-carbon piece. It doesn't matter if you use a bromide or an iodide or a chloride there, or a tosylate. It doesn't matter. You just bring in a 2-carbon electrophile, and you get your product. Very simple, very straightforward, very high-yielding chemistry. Now, if I want to take that further, in this example, I've got to take this down. What type of alkene is this? Is this a trans? Trans, and you know that to take an alkyne down to a transalkene, you can't use the Lindlar because that will give you cis. So you've got to use the sodium ammonia reduction, and that will give you trans. So what we've done there is our first example of what we call retrosynthesis. There's a whole lot of that coming in the second term. Looking at a product and then deciding how to make it. If you've picked up on the reagents this term, it's a lot of fun. Next term, we have a 37-step process that we have to get our heads around. Oh, look at that. What does that mean? I didn't bring enough what? Oh. That means I'm at the end of 10. Huh? We can go back to general chemistry if you want. I get paid regardless. but you might not be passing MCATs and PCATs and point after touchdowns and things like that. Right. I've got 2 chapters. I've got kind of 2.5 weeks to do this. The way the calendar works from now on, the schedule's a bit messed up. But we've got to finish 11, then finish 12. And then we're ready for the second term. I don't know what it is about this class. Do people take calculus 5 times to get through it? Probably not, right? People take this class 5 times sometimes to try and get through it. And it's because it seems to be a big bunch of a mess of information. And when you choose a textbook to try and teach the class, you have to be aware of that because, you know, Dr. Jackson, Dr. Jenner and myself have been doing this for our lives and our careers. But when you see it for the first time, it's huge. It's a massive, intimidating, messy subject. And our job is to try and clarify it. Well, the textbooks we used before the current one introduced this section, this material, in chapter 4. And this was a large part of the reason why people were just getting lost, because we spend some time talking about delta plus, and we spend some time talking about carbocations. And then within the same chapter, we jump to radicals. Radicals are related to those things, but they do very different chemistry. So one of the reasons I particularly like this textbook, it does have its faults, but I like this because it does it in a more logical way. You introduce all that plus minus stuff early on. You get used to it, you get comfortable with it, you apply it in chapter 7, chapter 8, chapter 9, and chapter 10, and then you come back into chapter 11. At this stage of the game, towards the end of the term, you know, the ones who are still left in the class are realistically going to get through the class if they want to, and they've picked things up. They know about electronegativity, they know about size, they know about strengths of bonds and stuff like that. They know about reversibility, kinetics, thermodynamics. So having this chapter now, I think, is just a better way to learn it. It is very different. It will do things, allow us to do things that we couldn't do with the other chemistry. In fact, it's all non-polar chemistry. We'll go back and talk about HBr with peroxides and understand why that doesn't give you Markovnikov addition, it gives you anti-Markovnikov addition. And we'll discuss mechanisms that are, I think, tricky, but because this is now towards the end of the term, should be, you know, in a more clear way. It should sort of fall out in a more clear way. Now, everything we've done so far involves this. And most of you can push those things in the right direction, or the appropriate direction, okay? Some of you, it looks like a fireworks display. Or it looks like John Madden, you know, all the X's and O's, and you go over here, and you run over here, and then we'll do an end around over there, and touchdown. It's a bit of a mess. But for most of you, including the soccer team, it's starting to make some sense. What was the final score? What were you, 0-12? Okay. Did you? Well done. We've got to now deal with a shift from the double-headed arrows to a new paradigm where we use the fish hooks. We use this arrow. They are very different. They don't look very different. That's why organic can be frustrating, because very similar things tend to, you know, they can have similar, different properties. We've got to move from 2 electron processes, nucleophiles, electrophiles, to 1 electron processes, radicals. Now, for anybody interested in medicine or pharmacy and biology, this is incredibly important because of things like free radical damage in DNA. Okay, free radical, this whole idea of generating radicals in the body, which then start to chop up your biological material and start causing mutations and problems. So we'll spend some time today and then Friday deciding that these things are genuine, they are real, they have certain shapes, and that they have very different mechanisms to the stuff we've already done. This is not SN1, SN2 anymore. This is, I think, more advanced, but hopefully more, you know, enjoyable. A radical is not a 6-electron species. Carbon typically wants to have 8. Carbocations, you had 6. Now we're going to deal with 7. It's going to have a spare electron, an odd electron. So in terms of the sort of systems that we've dealt with so far, everything we have done to date, acid-base chemistry, addition of hydroboration type reagents, ozonolysis, elimination to give alkynes, all that chemistry involved what we call heterolytic bond cleavage. And it involved nucleophiles and electrophiles and leaving groups. All of that is different now. In chapter 11, you're going to do something quite different. So that involved systems in which the 2 atoms that you start with, you identify a bond that is polar. Typically, you identify a leaving group, such as Y being more electronegative than X. And if X can handle a positive charge, like carbon can, you end up with things like carbocations and leaving groups, like in the SN1, the E1 process. Well, we're now changing gears. We're going to a system in which X and Y are similar in electronegativity, and some stimulus, let's say heat or even light, is put into the system, and you make the bond break. Now, this is completely logical. If X and Y have similar, if not the same electronegativities, they're going to break into the same pieces. Each is going to want one of those electrons. And this is called homolytic bond cleavage. And we're introducing now free radicals. Free radicals are reactive intermediates, just like carbocations were, but they do different chemistry. They have 7 electrons. They only need 1 more to get to their octet. We're not going to do nucleophiles, electrophiles. So let's get this right now. Let's understand this from day one. Up until now, we've dealt with that, double-headed arrows. If you're on top of those things, great. This chapter, we're dealing with these guys, 1-electron processes. Obviously, the next exam coming up in the final, it's a mixture of everything. By now, the hope is that you can differentiate between one and the other and do the appropriate reaction. Again, I can give you some hints, what to look for, but it's up to you to put the time in. So here we go. So far, we have dealt with carbocations. What shape are they typically? Flat, trigonal planar. Carbon has 60 electrons, therefore it's electrophilic. It wants to react with electrons to go someplace else. It is trigonal planar because that's the furthest away those pairs of electrons can get from each other. That's the VSEPR idea. This is 3719 so far. We haven't spent a lot of time over here, but we will in 3720. The idea of a carbanion. Now, why do you expect the carbanion to be trigonal pyramidal? Or why do you expect it to be roughly tetrahedral? Well, go on, carry on with that thought. It's similar to a carbon with 4 bonds, so therefore it's got 4 valences. Yes, 4 valences, 4 pairs of valence electrons means tetrahedral, or this is roughly the same as ammonia, NH3, where one of those is a lone pair, and that should be the same shape. So this is for a carbocation. We're all happy with that. This is for a carbanion. We will be happy with that. We now have to worry about what a radical looks like. If you can break a bond to carbon and give it 1 spare electron, where's it going to be? What's the orbital going to look like? And what shape will it be? So there are 2 arguments here. Either this thing is flat. Why isn't it tetrahedral? There's only 1 electron there. It's not a lone pair. Lone pairs will repel more than 1 electron. Or it could be 2 species which are converting into each other. This lobe gets bigger, this lobe gets smaller, and it turns into this. There are, as it says at the bottom, there's evidence for both, but we generally in this class will like this picture on the left. So radicals are flat. Radicals are trigonal planar. That will have really important consequences when we do stereochemistry. If this thing is flat, where can the next species attack from? Either side. If this thing is prochiral, what do we expect to see in the product? Racemic mixtures. Same ideas, right? Which is good, but also bad. Good because it's stuff you've thought about already, and then hopefully you've got your head around it, but bad because it's all starting to look alike. And if you dive into a problem on the upcoming exams and you think, oh, look, radicals, and it's a carbocation, it ain't going to work. So we've got to be careful. My friend Haldeman's not here today, so I'm going to have to pick on somebody else. The overall stability of carbocations was based on what? What makes a carbocation more stable? Hyperconjugation, which is? For those who can't hear at the back, it is the sharing of electron density from adjacent single bonds. You okay with that? They're okay with that. They agree with you. So it should make sense that if my electron poor thing, my carbocation, helps or is helped by hyperconjugation, surely a radical, which is missing 1 electron, should be helped by hyperconjugation. It is. So we find again that methyls are terrible. Primaries are not bad. They're not as bad as primary carbocations. And secondary are better and tertiary are good. So we'll see selectivity coming up, where we start to take off atoms at tertiary carbons, and they prefer to come off tertiary carbons than secondary carbons because the radical you get is more stabilized by hyperconjugation the same way. And we can see that manifested in bond energies at the bottom. The strongest bond here is between a C and an H on a methyl group. Strongest bond means it takes more energy to break it. It means the intermediate is higher in energy. It takes more energy to get there. Work your way across, significant differences here. It's getting weaker and weaker. This CH bond here on the tertiary system is weaker because the radical you go to is more stable, more stabilized. So those are things that are similar to what you've seen in the carbocation chemistry. We'll also see some interesting things now where even primary systems can benefit. Even primary systems are fine, and sometimes they're really good. This guy here, if you generate the primary radical on the end there and you have a pi bond next door, it's very similar to having an electron pair next door as we just did. It's very similar to having a lone pair next to a plus charge. You can help from next door. So I can swing electrons around here, and I can draw a resonance structure. And overall, this thing will look like this. It won't look like the two pictures on left and right. It will be delocalization of a radical, one electron. Not a negative charge anymore, which is 2 electrons, but 1 electron. So I'm going to introduce a new little thing here. Delta dot. Delta dot. That's just saying that the radical is spread across the whole system. Not delta negative, not delta positive, delta dot. 1 electron now is being spread around. So can you see where this is going? The carbocations, you're missing 2 electrons. The anion, you have 2 electrons. This is in the middle. Yeah? Carbocations, 6 electrons. Radical 7, carbanions 8. So we're now in the middle. Second semester. You're not going to see a lot of this term. I'll talk about it in terms of why it's good to do this reaction at a benzylic position. But this position outside a carbon cycle, outside this benzene system, is highly activated. That's called the benzylic position. You should know these two names. Top is allylic, which we've seen many times from the resonance stuff. Down at the bottom, benzylic. And that is a benzylic radical, which is pretty good. You won't be able to isolate it because it's going to react and go someplace else, but it's getting better. Why is this so good? Look at all these different resonance structures I can draw to get there. Now, something I do in recitation coming up, and we'll do recitation today and next week, we're going to talk about why only reactions happen here. And even though we have some radical there and we have some radical here, the only reaction actually occurs outside that cycle. It's because you want that benzene back. For reasons to be revealed in enormous detail next term, 2 whole chapters of this stuff, that benzene ring is good. Okay? There's the IUPAC symbol for good. You want that benzene ring back if you possibly can. So you only react there even though it looks like a radical delocalized system. They're good. Even though they're primary, they're good because they've got help from next door. And in fact, we'll summarize that by saying hyperconjugation is good, radical delocalization or delocalization in general is better. You got both of them, you're in good shape. So look at these systems. We've got now nuance, subtlety. You've got to be on your toes here. Look at the bond energies here. For a tertiary CH bond in 2-methylpropane, the bond energy for this CH bond is 406. Even though this is a primary system, the bond energy for this is 364. That's a weaker bond. This is easier to break. If you go across to this system over here with the benzylic, 356. This bond, even though it's a primary system, is easier to break than this tertiary bond. Don't forget, this is all about where you're going. We're going to see reaction profiles again. You start down here, you go someplace. The higher that place is, the stronger that bond, the harder it is to break. The lower that gap is, the easier it is to break. So for some reason, which we've just talked about, the idea of resonance, this bond here is easier to break than over here because the radical you go to is more stabilized. That's very subtle. So even though it's primary, it's benzylic, and that benzylic makes the difference. So we need to identify some things here to get going in the chemistry. Spend most of today defining some things, and then on Friday, and you've got now stop it down there. You've got 3 days to actually get this stuff in your head and start to understand it. There is a big difference in the chemistry of these two positions. Directly attached to a cycle out here are called allylic positions. I'm sorry, on an alkene. If you are actually the carbons in the alkene, they're called vanillic. Now, all the chemistry we're going to do in this semester, or this chapter so far, really is there. That allylic position benefits from resonance. It does not benefit from resonance on the right. So you're looking for allylic systems, you're looking for benzylic systems, and they're particularly good for radical chemistry. So again, there are your numbers. Recognize here, a CH bond on an alkene is very strong. A CH bond on a primary system is weaker, and a CH bond on an allylic system is weaker again. You do not want to put a radical here because there's no benefit from resonance. Here, you benefit a little bit from hyperconjugation. Here, you benefit from resonance. So it adds up and it's logical. You should be able to see the differences there. Anybody? 3720 left as well. It's going to be great. Okay. Let's think about some of the similarities and differences between carbocations and radicals. And looking at the roster, looking at who's in the class, a lot of you need to do biochem at some point. And radicals are important in biochemistry. Some things that carbocations do that radicals don't do, for example, will be rearrangements. Radicals won't rearrange, at least in this class, at this level. Carbocations on the left have this annoying propensity to want to rearrange because they want to become more stable, so the skeleton changes. That can be good if you understand the process. It can give you a product that's useful, but often it gives mixtures. That's not very useful. But radicals are a little bit more reliable because they don't do that type of chemistry. So we're going to go to the same sort of places. We're going to turn alkanes into bromides, and we can predict where the bromine will go based on stability of the intermediate radical. So that can be very useful once we understand how this happens. So we'll start off. My goal for the end of today, just to get through this, is to talk about these types of bond processes. And then on Friday, we'll do radical halogenation. And radical halogenation is like nothing you've seen so far. Let's see if we've picked anything up over the past few weeks. If I do this, and I tell you this is something like OO or BR-BR, what can you tell me about that bond? It's weak. Yes, it's weak. So it should break fairly easily. And we'll now see some logic applying. If you have a mixture of, let's say, an alkane with CH bonds and a bromine molecule, BR-BR bonds, and you heat this stuff up, which one breaks first? The bromine bonds, of course, because they're weaker. So when we heat the reactions up, which is this symbol here, this is heat, and this is light, they both work, you get homolytic cleavage. And that is typically the first thing that needs to happen to get these reactions to go. Now you can see that we did this sort of when we did the possibilities for bond-forming reactions earlier. We did proton transfers, we did nucleophilic attack, we did leaving groups breaking off, we did rearrangements. Those 4 different arrows for those types of heterolytic systems. Now we're defining the systems for homolytic system, the idea for homolytic system. So this is a weak bond, no doubt. That's a BR-BR or an OO bond, something like that, and that one thing will pop apart. And it will break to give you 2 radicals. Why did it do this? Because the 2 atoms that you start with on the left are about the same electronegativity. So neither of them has a real hold on both those electrons. They're going to take 1 each. Well, once you've done that, you know, the cat is amongst the pigeons, whatever you want to call it. This thing now is going to be problematic. Those things are little buggers. They're going to go after anything they possibly can. They're very, very reactive, and they will cause mayhem. One of the things they can do, if you have a pi bond present, is go after that pi bond. When I teach the radical reaction on Friday, you'll see that this requires quite a bit of thought outside of your comfort zone to get your head around this system. You can add to a pi bond. Why? Well, pi bonds are weak, and pi bonds have electrons. And what a radical needs most of all is 1 electron. There's a shift. Carbocations needed 2 electrons, that's why they reacted with nucleophiles. Now we have a radical, needs 1 electron. Go after a pi bond, pick up 1 electron. Well, if I do that, I've got to be careful. I've got to use the correct arrows, which means single-headed arrows, and I've got to recognize that there's 1 electron here and there are 2 electrons here. I can't just ignore the 3rd one. So when I pick up 1 electron to form a bond, this is the bond that's getting formed, that will help out the X, no problem. That will give you a nice bond, and it will stabilize X. But there's your 3rd electron, right? You've got to keep a track of 3rd electrons, of the 3rd electron. I've got 1 from the X, I've got 2 from over here, that's 3 total. There are the 2 of them, there's 1 left over. That's a new radical that you've just formed. And that new radical is on carbon, which might have something different about it in terms of its stability and its structure than X originally did. So yes, of course, if something needs an electron and pi bonds are around, go after a pi bond. Pick up an electron, form a bond, away we go. Something we haven't seen. I guess it's similar to an acid-base reaction, but it certainly isn't an acid-base reaction because we're not dealing with charged species now. This radical can go after a carbon-hydrogen bond in a process called abstraction. And that abstraction now involves X again being reactive, finding some bond that is weak enough to be able to strip off a hydrogen from it. So on Friday you'll start to see this idea of the hierarchical system where tertiary bonds tend to break faster than secondary, faster than primary, because you get a better tertiary radical. But over here now we have products in which we've taken 1 radical, we've produced something that is stable, and we've produced something else that is a radical. We'll call this a propagation step on Friday. We take 1, we react it with something, we produce something new, and we produce a new radical. This probably is happy now because it became neutral, it became stabilized, but this thing is reactive. It goes on someplace else. We're going to see radical chain processes in which this thing keeps going and going and going. So that is hydrogen abstraction. Halogen abstraction is the same type of deal. Looking at this, if this is bromine, there are lots of electrons to be had. Now I can't just rip off an electron. We're not doing any ionization chemistry here. You can prove that through the mechanisms. We're not doing anything like making X plus or C minus or anything like that. It's all radical based. And so what's happening here is that the R radical is taking an X atom with it and one of the electrons from that bond and producing a stable product. But the problem is, the sort of quid pro quo for that is that you get this radical as well. Okay? You get that as well. All right. You get this radical back. So these two steps have a lot in common. You consume a radical here, you generate a radical on the right-hand side. You consume a radical here, you generate a radical on the right-hand side. And for those of you who are starting to catalog things and keep a track of these things daily, that will be important. They will be very similar steps. Something that you need to be aware of. You can also get rid of the leaving group, or be careful here, get rid of the halogen through a reverse process. We'll find now that addition of radicals to double bonds is actually a reversible step. So what I can produce here is a radical that can go backwards. And that will be key when we start thinking about, well, bromine did this over here with the alkene. Why is it doing this over here now when it's a radical? We'll have to argue that on Friday. So I can go backwards from this species and produce the alkene back, and I can get my halogen back. And that's viable. That's a reasonable process. And the last step is coupling. And when the chemical engineers are back, we'll talk about this as being detrimental. This one is a bit of a problem. It's a bit of a nuisance. When we talk about the reaction on Friday, it's one of these maybe perfect things in which you just start by heating it up for 5 minutes, and it just goes, and goes, and goes, and goes in a cycle. And every time you generate a product, you get some radical back, and it keeps going and going and going. Unfortunately, you can't do that because these radicals tend to find each other, and they tend to couple. Because this has one electron, this has one electron, and this is a neutral molecule. So if they find each other, they're going back to this system. That won't be a problem because we're continually heating this stuff. And if that's a weak bond that I'm continually heating, it'll go back to radicals. What we've just done is laid out the possible processes for what can happen with radical chemistry. So to finish up, you've got a lot of work to do between now and Friday. We can call this initiation. The radical reactions will not happen unless you initiate them, unless you start them. And to start them, you have to break apart a weak bond, for example, on a halogen. That will give you radicals. Once you've got radicals, away you go. The games begin. You've got the addition possibility, if you have an alkene in your molecule, of adding to that alkene. That gives us a new radical. You have the possibility of your X radical taking off a hydrogen from an alkane. That gives us a carbon radical and a neutral product. Over here, we can go after a halogen, and we can produce an alkyl halide and a new X radical. Or we can eliminate, and that gives us those starter materials back. Finally, we can do a coupling in which two of those things come together to give us a neutral species. The problem, well, not the problem, but the categorization here. You need to start the reaction by doing that, initiation. This allows the reaction to continue or to grow, propagation, and this will stop the reaction, termination. Now, do yourselves a favor. Read that stuff before Friday, because what I'm about to do is just, yeah, it's tricky. Okay? So come and find me if you need to talk, and we'll see you on Friday.